today we are going to look at what actually happens with these electrons and the orbitals that the electrons are in when we make these covalent bonds. And so before we can really get into that, we need to talk about some things that we maybe talked about a couple chapters ago. So first of all, covalent bonds form when the electron clouds of two atoms overlap. So that's shown right here. And this overlap space is where the newly paired electrons will reside. A covalent bond will form when unpaired unpaired electrons form from two atoms match up. Overlapping orbitals do not have to be the same type. By same type, this is an s orbital down here where this is a p orbital. So you don't have to just overlap two s orbitals. An s and a p orbital can overlap. This leads us to the valence bond theory, and that says that covalent bonds are formed by the overlap of partially filled atomic orbitals. So this brings us back into electron configuration, not dot configuration, but electron configuration. This is where we drew the circles like the 1s, and then it went to 2s, and then 2p. Remember those circles? And we filled in electrons that way? Yep, so that's what we're going to look at today. So I want to practice this by drawing the electron configuration for carbon. So the electron configuration for carbon would be 1s2, 2s2, and 2p2. Okay, so to draw that, we draw our 1s orbital, then we have a 2s, and then 2 p's. Remember, the p orbital has three different orientations. That's why there's three different circles. Then we follow the rules. We have to fill our 2s with 2 electrons. Our 1s. Then our 2s also has 2 electrons. Why, remind me again, why is there an up arrow and a down arrow, Cora? Yep, it shows that they have opposite spins, and they must have opposite spins. And then when we go into the 2p orbital, do I fill both electrons in this first orbital? No, I only put one, and then the second one will go in the second orbital. So according to the valence bond theory, it says covalent bonds are formed by the overlap of partially filled atomic orbitals. So, how many, according to this drawing up here, how many bonds can carbon form? How many are partially filled orbitals? 2 are 2p orbitals. So, however, if we drew the dot structure for carbon has how many valence electrons? 4. 1, 2, 3, 4. How many bonds is carbon actually able to produce? 4. So we know it can produce 4. So, but the electron configuration says it can't. How does this work? What has to happen? If you read like the next 2 bullets, you could figure it out without hurting your brain too much, or you could try and figure it out without cheating. That's an option too. Oh, Studi. Holy crap, you have your iPad today too? That's awesome.
Yeah. So you take
an arrow which represents an electron.
Yeah. From the S and bring it to the P.
Yeah, this electron gets promoted into this orbital. Okay, that's called electron promotion. When electron promotion happens for this particular element, we still have our 1s, That is completely filled. Then our 2s now only has 1. Then we go into the 2p, and we have the 2 that were originally there. And then we have to put the electron from the s sublevel into that p level. Does that make sense? Now, how many bonds does this diagram show that carbon can produce? 4. Okay? So electron promotion requires some energy in order to remove the electron from here and move it to that 2p orbital. Okay, so we're just rearranging our electrons. So when we do electron promotion, we get something that is called hybridization. This is the mixing of atomic orbitals in an atom to produce a set of hybrid orbitals. We can mix non-equivalent orbitals. By non-equivalent, what that means is you can mix s and p orbitals. Like I said on, I think, the first or second slide, it doesn't have to be between 2 s's or 2 p's. You can mix between an s and a p. So the s and p orbitals can hybridize, but p orbitals cannot hybridize with other p orbitals. That's because you're changing energy levels then. So back here when we did the electron promotion, both of them were in the second energy level, so that's okay. Does that make sense? Whereas if we wanted to promote this p electron to another p orbital, we'd have to promote it to the third p or the 3p, and that's just not possible because we're skipping too many steps. It's not right next door. Does that make sense? What would be the next orbital to the p orbitals? Okay, the 3s or the
2D.
the d orbitals, yes. So p's can promote into the d orbitals. Hybrid orbitals are atomic orbitals obtained when 2 or more non-equivalent orbitals from the same atom combine in preparation for bond formation. So this is exactly what we just did. Here's carbon originally. Here we promoted. And then our final hybridized orbital gets written this way. So notice now instead of there being a step, they're all in the same row. And we don't separate out the S and P anymore. We call them sp3s or 2sp3. Okay. This 3 indicating that there are 3 p orbitals involved. And the basic rule of not writing the 1 with the s because there's only 1 orbital there. So when you draw it out, here's what your normal s and p orbitals look like. When you hybridize them, you will notice that there is a slight change to the shapes. They kind of mash together and average out, so to speak. So to do these problems, your book says to do all of these steps. Draw the Lewis structure, use the Vesper theory to predict electron domain geometry and molecular geometry, and then match the electron domain geometry to the appropriate hybridization, blah, blah, blah. It's a lot of work. Do it my way. For once, my way is slightly better. You can do it the book way, but that seems like a lot of work to me. My suggestion is to look at your formula. So let's just pick one. Let's just do BF3. So given that formula, figure out what your central atom is going to be. In this case, what's our central atom? Boron. Okay? And the 3 fluorines are going to come off of it like this. Yes? Okay? So determine the electron configuration for that central atom. So boron is 1s2, 2s2, oh my goodness, 2s2, 2p1, okay? So we don't really need to worry about drawing the 1s sublevel since none of those electrons would promote. We need to have how many open orbitals to form these bonds here? Oops, I didn't mean to make that look like a double bond. We have 3 bonds, so how many open orbitals do you need? 3. So here we have our 2s and then 2p. And so originally our 2s is completely full with 1p. Do we have enough bonds or orbitals available? Nope. If you don't have enough bonds or enough orbitals available, you have to follow step 3, which is promote an electron. So we'll take one of these and move it into here. So then we have our S and our 3 P's, and there's 1, 2, 3 electrons. Okay? Does that make sense? Okay? Then if you need to look at this chart to figure out the specific answer about the geometries of the molecule. Since I've been providing you with charts to determine your molecular geometry and your electron domain geometry, I will continue to provide you with this chart. You probably won't see this column, though, on a test or a quiz. Okay? Any questions about how to do this electron promotion? Yes?
I understand how to do it, but I don't understand why we have to move them.
Why you have to move them? So bonds can only take place in orbitals that only have 1 electron. Okay, we can't overfill an orbital. And so when we only have 1, in this particular case, there's only 1 half-filled orbital. We need to make 2 more half-filled orbitals to get our total of 3. Does that make sense? And so to do that, we zap the molecule with a little bit of energy, take one of the electrons from a lower orbital, and shove it up into a higher orbital. Does that make sense? That's what you needed?
Yeah.
All right, lovely. Yep.
So what would be like the geometry thing for this one that I don't understand?
So the geometry of this one is, it looks like how many hybrid orbitals did we make? 3. So I would look here. Your electron domain geometry would be trigonoplanar. And then possible molecular geometries could be those 2.
So it's SP2 because
Be-
there's
We...
S and SP.
Yep, because we filled, or we hybridized, we're using 1 s orbital and 2 p orbitals. This third p orbital remains blank, so we can't account for it in this hybridization.
Okay. We don't count the 1s2.
Correct, we don't count the 1s2 because it's not involved with the bonding, because it's not the valence electrons. So yeah, with all of this, you're only, the drawings, when it asks for these drawings, I'm only concerned about seeing the valence electron ones. A couple other things about hybridization is elements in the 3rd period and beyond can expand their octet. This requires hybridization into the D sublevel. Example here would be PCl5. Phosphorus is in 3s2, 3p3, which is drawn here. But in this case, we need to make 5 bonds, and we only have 3 open orbitals for that. So we're going to promote this 3s electron into the 3d sublevel. So that's where we expand the octet into. Does that make sense? We kind of said something about that already. Other things, double and triple bonds. This is more just of an FYI. Sigma bonds and pi bonds are fancy names for double and triple bonds. Sigma bonds will form when the orbitals overlap end to end, like this. And the electron density is concentrated between the nuclei of the bonding atoms, so the electrons are in here, in between the 2 nuclei. Pi bonds form by overlapping of orbitals in a side-by-side fashion. Electron density is concentrated above or below the plane of the nuclei. So that would be kind of up here when they, right here would be one. Any questions?